summary of conic sections. After you kind of learn conic sections, it's really good to kind of look at the big picture and put it all together and understand all of them and the comparisons and differences between all of them. So we're going to talk about all four conic sections real quick. I'm going to go one by one through each of these and describe each one and then put them all together and summarize them all together. So again, we have parabolas, we have circles, we have ellipses, which are kind of like ovals or squished circles, and we have hyperbolas, which kind of look like two parabolas going opposite directions, but it's not a parabola. I sometimes call this the cracked egg. Here's your egg, here's your cracked egg, because if you look at these two formulas, they're very similar. So here we go. Let's talk about parabolas first. This particular parabola, here's the equation for it. All right. We generate parabolas from these two. Now, why is this one an x equals? Because we have two choices. Well, since the graph is going to the side, it's going to be an x equals. If the parabola is going like up or say down, it would be y equals. But this is the x equals. And then all we need to make the parabola is the a value and hk. They both have an a and hk. So hk is the vertex. See that right there? The vertex is 1, -2. The a value is a little bit hard to figure out. We're just going to focus in on the negative at this point because it's going in the negative value of the x-axis. If it was going this way, it would be a positive. Or just trust me, it's -1 for now. And then, so you basically plug in your hk and your a value into this formula, and you get the equation of the parabola. Again, if it was going up or down, you'd plug those values into this formula. Just depends on which way it's going to which formula you need. All right. So parabolas, probably the more difficult one to graph. But one thing you can always know about parabolas, like you can spot them pretty easily by equations, is they're the equation with only one squared piece. All the rest you'll see have two squared pieces. Next one, the circle. My favorite, and probably yours, it's really easy. There's only one formula. You have your hk, which is the center. See this center right here? 2, 4, hk, 2, 4. If you see right here, you see the radius, 5 in all directions. So we got the radius and the hk, and then you see hk and r. Do you see we plugged them in? Remember, it's always the opposite of h. Negative k means opposite of k. So we take the opposite of 2 and opposite of 4. See that right there? You square them, and then you square the radius. So if you see this, you also need to be able to graph it. You have to go backwards. Sometimes you have the graph to the function, sometimes you have to do the function to the graph. So if you had this, you'd look at the 2, 4, put the center, and then you would go radius of 5, the square root of that, go 5 in every direction. So it depends on which way they ask you the question. Sometimes, again, they'll give you the graph to function, sometimes it's the function to the graph. All right, so circles, one of the easier ones. Next we have the ellipse, which is kind of the egg shape or the squished circle. There's two different possibilities here, but the only difference between these two is where the A and the B are. All right, so we kind of got to talk about what A and B is. If you look at this answer down here, hopefully you actually probably can't tell, but this is the first one because A is basically your larger value. All right, in this situation, the larger is the first one. So, or the one under the X, which is more defined than the first. So, but they always have a plus, they always have equals 1, they always have numbers underneath. And so, see the HK, do you see the A, but now we have a B. All right, so we have A, B, and the HK. All right, HK again is the center, so if you can see the center right there, 3, -2. Now where does 6 and 3 come from? From here, do you see how we went up 3 for that kind of radius, if you think of it? Like the short radius. And then you went 6 over in both directions from the center. That's kind of the longer radius. Now where did 36 and 9 come from? What's 6 squared? What's 3 squared? All right. Now, why does the 6 go here and the 3 go here? Well, what you do is you look the 6. Do you see how the 6 here went in the x direction and the 3 went in the y direction? So when because the 6, the radius goes in the x direction, do you see how the 6 went under the x? Since the y is 3 up, do you see how the 3 went with the y? So you kind of got to watch for that, that the number underneath relates to the letter above. That's huge. So here, that's why we're using this one, because the A value is the longer radius or longer kind of stretched side. So that's why this equation is actually one we're using. Now if this like egg was going this way, kind of a long way this way, the bigger value would be under the y and the shorter value would be under the x. So you need A and B to get kind of the stretch or the radiuses, and always equal 1, and then hk. And again, it's always opposite of h, opposite of k. Just watch out for those opposites. Alright, last one, the hyperbola, the cracked egg, I call it. Now hyperbola has these little lines called asymptotes to help you graph. We'll talk about those, how they're kind of generated and stuff. But basically, these little asymptotes aren't part of the graph. They just kind of help you graph it and kind of give you your parameters for graphing, like little, they just help you graph, basically. Anyways, hyperbolas have minuses. If you notice, you have a y here first and an x here first. Now in this particular one, do you see how the y is first and then the x with the minus here? Well, the reason the y is first and the x is second is, you see how this hyperbola is opening up and down? Sometimes hyperbolas open side to side. If they open side to side, then it would be this function. The x is first. All right, the a is always the first one. The b is the second one. It's not about the big and the small like on ellipses. The a is just always first on hyperbola. The b is always second. But so we're going to use this function. So we have our hk, our center, right there, bam. And where do we get 4 and 2? Well, if you imagine these little x's, what you do is from the center, 2, you went over 2, and you went up 4. Basically, you create a little box here. To graph, you create little boxes by the a and b. Okay, so you went up 4 and over 2, creating a little box. And do you see if I made a little box like that? Do you see how those height asymptotes go through the box? So what you're going to do basically is make a little box by your a and b, and then you make your asymptotes through it, which help you graph these hyperbolas. Once I have that box, once I have the asymptotes, bam, you just graph those right inside. An asymptote basically is a boundary marker that the graph can't touch but goes up against really close to. Anyways, so the 4 is the y value. See how the 4 squared goes under the y? And the 2 over 2 squared is 4, is under the x value. And then, again, the y is first because it's opening up. If we're opening to the side, the x would be first. And then it's opposite of h and k. Except, real quick, this is k, this is h, k, h. Because the y always has the k, the x always has the h. You just got to keep track of those. X always goes with h, y always goes with k. Which way is it opening? They always equal 1. Alright? And again, there's this box thing which helps you make your asymptotes. So, there they all are. All 3 graphs. Hopefully you see the similarities between these. Plus, minus. They all both equal 1. This has a y first, this is an x first, depending on which way you open. This is always x first because the plus, the order when you plus doesn't really matter. But the a value is your biggest number here. Over here your a value is your first, the direction you're opening. Here you don't have an a and b, you just have your radius. And here you have an a value, which is kind of your width of your parabola, and then hk is your vertex. So hk can be your vertex, but in these it's the center of all of them. So they're all very similar, and you got to be able to kind of make a comparison. You got to be able to like see these equations and be able to graph them. You should be able to see a minus and go, oh, it's a hyperbola, a plus with an equal 1. Ah, it's an ellipse. And then look at my hk. This is for 36 means I'm gonna, for my x, I'm gonna go out 6 for my hk. Anyways, there's a lot of little things. I'm just trying to give you an overview of it. Hopefully all this stuff is kind of making some sense since you have a little exposure to conics already. Alright, one more thing. Let's do a little applications of conics. This is pretty cool, an application situation. Conics have focal points. Right here is my focal point. On an ellipse like this, I have 2 focal points. On a hyperbola, each one has their own focal point inside. All these have special reflection abilities. For instance, reflection happens with, for instance, mirrors. If I have this going right here, like this, and then if I have some light coming in, say this is a mirror, if I have light coming in, it's going to reflect to that focal point. If I have light coming in, it's going to reflect to this. If that was a wall, sound would come and bounce off and come here. Any sound coming in would bounce off and come in there. Now, by the way, it has to come directly in, not at an angle, but directly in, and it'll always reflect to there. So what happens is this harnesses all sound or light or whatever you're trying to reflect, light or sound, and goes to the focal point. It's a great way for making energy. And you see solar cells. This is how they make, that's not solar cells, but they make energy by heating tubes of water that sit right here with a whole bunch of mirrors. You might have seen that before. Now think of this as a lens, like a contact or a magnifying glass. All light that comes directly in gets refracted to that point. All light that comes in gets refracted to that point. Focal points are huge in lenses and reflections and sound and tons of situations. And you'll learn about focal points when you deal with conics. I didn't talk about it in my previous video. But anyways, here, a cool thing about ellipses, let's say this is an oval room or an oval pool table. Let's talk about pool table first. If I have my ball here and a hole here, if I hit this ball against any wall, it'll bounce right there. See these lines? Boom. It's going to go right there. If I start here, hit it, boom, it goes right there. So if you're in one of these spots, it will always go to the other spot no matter where you go, what wall you hit it at, as long as you don't have English and it curves. Okay, with that said, what about if you had a room that's oval? If you put a chair here and a chair here, you could have a little conversation between the two of you because all your sound would bounce off every wall and come to each other. So people can be all walking around talking and you can have a little conversation with each other. Kind of weird and trippy, but you could. Reflections are interesting. Last one, hyperbola is a little interesting here. For instance, let's say you are right here and you are looking at this focal point over here. Okay, or you're trying to shoot this focal point with like a pool ball. All right, you're trying to shoot, look at this one, and this is sitting right here. So if you aim at that one, anywhere you are, if you aim at that, it will bounce and go to this focal point. For instance, if it's right here, and I try to hit that, aim at this guy over here, it would go boom, focal point. Another example is if I aim at this focal point, and pretend this one's not here for now, pretend that light's not there. If I aim at this one, hits that, and it'll go to this focal point. So like for instance, if I'm up here and I aim down here at this point, it's going to hit this and go to that focal point. It's just really interesting how this reflective properties apply to conics. Hopefully that kind of makes some sense and gives you a little application of why conics are useful.